Now we'll begin Chapter 6, Applications of Definite Integrals. In this chapter, we'll study definite integral techniques for the computation of a volume using cross sections, volume using cylindrical shells, and also we'll study how to get arc length and areas of surfaces of revolution. And finally, we'll study how to get work even when the force is not constant. Let's go to section 6.1, volume using cross sections. Suppose that we want to find the volume of a solid S as given in this figure. The solid is occupying the space in x direction from A to B. For each point over the interval, you can form a cross-section by cutting the solid with a plane perpendicular to the x-axis. Now, we can find the region, the area of the region here. Let's say there is A of x. Now, in this section, we'll show that if A is a continuous function of x, then the volume of solid is the definite integral of the cross-sectional area from A to B. The method is known as the method of slicing. Okay, let's drive the method here. The first step is partitioning of the interval. We'll use the technique of Riemann sums. By taking limit of Riemann sums, we try to get the volume. So start with a partition. Then for each subinterval of AB, you can get here thin slab. Now the slab can be approximated by a cylindrical solid. For example, now you can make here area, cross-section, area of this cross-section at xk, and consider the here cylinder in x direction. Then the cylindrical solid is approximating the original slab. Here, the volume of the kth slab can be approximated by volume of the cylindrical solid, and that is A xk times delta xk. Delta xk is this length. It's used as height, and area, base area times height. Now, if you sum over the subintervals, then it will become a Riemann sum. Now, by taking limit as n approaches infinity or the partition length approaches 0, you can get the volume once the limit exists. Here we define volume. The volume of a solid of integrable cross-sectional area A of x for x over A to B is integral of A over the interval. That is Riemann sum, and limit of Riemann sum. It can be written here integral from A to B A of x dx. Now, when you meet a problem finding volume of solid, then you can use this strategy. First, the sketch the solid and try to find the typical cross-section and find the limit of the integration, and here lower limit and upper limit. For each x over the interval, find a formula for the area and integrate ax over the interval to get the value. Let's see this example. A pyramid 3 meter high has a square base that is 3 meters on a side. Find the volume of the pyramid. Okay, if we consider this picture so that we make a sketch and try to find the limits of the integration from 0 to 3. And now for each x from 0 to 3, and for each x, now we have to find the area. But the problem is given with the pyramid and height 3 and on the bottom and the base side length of 30 meters, so that at x over there, the side will be x. So the area must be x squared. Now we integrate the area from 0 to 3. Area is x squared, so that we can get the final answer. Let's go to another example. A curved wedge is cut from a circular cylinder of radius 3 by 2 planes. One plane is perpendicular to the axis of the cylinder, and the second plane crosses the first plane at a 45-degree angle at the center of the cylinder. Now find the volume of the wedge here. Now, cylinder is given in this way, and big circular cylinder is given. Now cut here, and along with a 45-degree angle is cut, so we can get a wedge. Okay, for that one, if we consider that is x direction, then if you look at the wedge from the top, then you'll see this way. Here, that is now given in this way, and here, that is x direction. Now, radius 3, so that it will occupy in this way. That is now 3. And if you look at the wedge from top, it will be seen in this way. Now, that is not sketch, and you can find the lower limit is 0 and upper limit is 3. Now, for each x of the interval, you have to find the area. So the area is now depicted in this way. So that is x. Then, because that is a 45-degree angle, the height will be x. For x, now you have to measure the length from here to there. For each x, now we know that the height is x. Now you have to measure that length. That is exactly this one. But this is circle of radius 3, so that is now y equal plus minus square root of 9 minus x squared. Top one, for each x, top one is plus square root of 9 minus x squared. Bottom one is minus square root of 9 minus x squared. So that length will be twice of square root of 9 minus x squared. So area at each point will be x is height, then that is now the base length. Okay, so it is 2x square root of 9 minus x squared. So the volume can be obtained by integrating a of x from 0 to 3, and that is 2x now square root of 9 minus x squared dx. Let's try to use substitution technique. U equal 9 minus x squared. Then here du equals same as minus 2x dx. So dx, okay, 2x dx will be changed with, replaced with here minus du. And here x equals 0, the bottom x is moving from 0 to 3, and now x is 0, the lower bound, then 0 means u is 9. Okay, if x is 3, then u must be 0. So the given integral is changed into bottom limit is 9, upper limit is 0 for u, and this portion is u to the 1/2 power, and 2x dx here is minus du. Right? So if you want, then you can rewrite this one from 0 to 9 and u 1/2 power and du. Now, integration of that one is not difficult for you, so you can finish the computation. Okay, that's the end of the part 1, and we'll continue in the second part. Thank you.